Good afternoon, everyone. In this final work, the goal of this project was to predict whether loan applicants would default on a loan. In this dataset, the target variable is binary. A value of 1 means the applicants defaulted, and a value of 0 means the applicants repaid successfully. This is not just a normal classification problem, it is also a high stakes decision problem. A model like this may affect whether someone gets access to credit. So in this project, I did not focus only on prediction accuracy. I also look at fairness, explainability, and ethical impact. This is why responsible AI is central to this notebook. I will walk through my work in 5 parts. First, I will explain the data and the preprocessing. Second, I will discuss the model and the validation result. Third, I will explain the interpretability method I use. Fourth, I will talk about the fairness and the responsible AI metric. Finally, I will close the ethical analysis and production readiness. So let's start with the data. I use the main application level home credit dataset. It contains demographic, financial, and behavioral features of each applicant. The data also has many missing values, and the target is highly imbalanced. Based on the assignment description, only about 8% of applicants are possible cases, meaning they defaulted, while about 92% are negative cases. This imbalance matters a lot. If I only look at accuracy, a weak model could still appear good by predicting the majority class too often. Because of that, I use several metrics, including ROC, AUC, per session, record F1 score, and something else. During the pre-processing, I first explore the dataset and check the missingness, class balance, and the basic feature distributions. Then I handle data types and some known anomalies, such as the unusual values they employed. After that, I separated the target and ID column from the modeling features. For the missing data, I use a selective strategies. I dropped the columns with more than 70% missing value because those variables were too sparse and would add too much uncertainty if I put it down. For the remaining columns, I handle the missing value inside the preprocessing pipeline. I use median imputation for numerical features and most frequent imputation plus one hot encoding for categorical features. This approach let me keep useful signal while removing the least reliable variables. Next, I split the data into training and validation sets. I use a handout holdout validation approach, which is allowed by the assignment rubric. My first model was logistic regression. I use it as a baseline because it is simple and easier to interpret. My second model was the random forest. I chose that because it can capture nonlinear relationships and interaction between features better than logistic regression. Now I will discuss the performance. The logistic regression model serves as a useful benchmark, but it did not perform near as well as random forest model. The stronger model was clearly random forest. On the validation set, the random forest model achieved a ROC AUC of about 0.974. Its accuracy was about 0.922. Its precision was 0.5, and the record was about 0.913. The F1 score is 0.646. The results are important because they show a strong balance between identifying true features and keep overall classifications performance high. In the confusion matrix for the random forest, the model correctly identify 84 true positive and 996 true negatives, with 84 false positive and only 8 false negative. In a credit risk setting, false negative are especially costly because they mean missing applicants who are actually likely to default. So having only about 8 false negative is a strong result. After evaluating model performance, I move into interpretability. The assignment asked for both global and local explanations, so I used two explainability models. First, I used the random forest feature importance for a global view. Second, I use SHAP for both of them. Uh, from the future important result, the most important variables were exit source 2, the source 3, source 1. Other strong features include the day birth, the day last phone chance, day employee, the AMT credit, the day's resignations, day ID published, and the AMT annuity. This makes intuitive sense. External risk scores, age-related information, employment history, and credit amount are all responsible predictors of repayment risk. The result helps show that the model is using meaningful financial and behavior signals rather than random noise. For SHAP, I use a summary plot to understand the global patterns across the validation sample. This helped me see which features had the largest overall impact on predictions and whether they push the risk upward or downward. I also use the SHAP waterfall plot for one individual applicant. That gave me a local explanation and showed exactly which features increased or decreased predicted risk for that case. This is useful for responsible AI because it improves transparency. It allows us to say not only what the model predicted but also why it made that predictions. Next, I will look at the fairness. Because this is a sensitive domain, I orient the model by gender using two fairness perspectives. The first was a demographic party style check. The second was an equalized odds style checking using TRP and FRP. For the demographic party result, the predict positive rate was about 10.95% for male applicants and about 20.53% for male. For the equalized odds view, the true positive rate for female was about 0.87837, while the male is about 1. The results suggest that the model behavior differently across gender group. That does not automatically prove the unfairness, but because the base default rate are also different across group in the data. Now I want to briefly discuss the ethical consideration. This model could create harm in two ways. A false positive could wrongly label a reliable applicant as high risk and reduce fair access to credit. A false negative could allow a high risk loan to be approved and create losses for the lender. So neither type of error is neutral. Finally, I want to mention the production readiness. If this model was deployed in a real lending system, I would recommend ongoing monitors for data drift and the fairness. I would also review the threshold regularly instead of keeping them fixed forever. To conclude, my project built a credit default classifier that performs strongly and also addresses the responsible AI goal. The random forest model clearly outperformed the largest regression baseline. I validated the performance using holdout testing and multiple metrics. I used the feature importance and SHAP for global and local explanation. I audit fairness by gender using demographic party style and equalized odds style. I also examined the strategical choice through the cost of false positive and false negative. Thank you, that's all.